Welcome back to The Explainer. If you're looking to understand exactly how critical tech industries are evolving right now, well, you're in the perfect place. Today, we're diving into Nanhua University's bachelor program in semiconductor application, or the BSA program for short. We're going to explore how this specific educational pathway is tackling massive bottlenecks in the semiconductor industry, literally bringing green technology right down to the factory floor. Here's our roadmap for today. We'll start with 1. Breaking industry technical bottlenecks. Then unpack 2. The PSIG platform framework. From there, we'll shift gears into 3. Green semiconductor manufacturing. Take a deep dive into 4. The carbon capture process. And finally, pull back out to look at 5. The net zero reality. Let's jump right into section 1. Breaking industry technical bottlenecks. So, Nanhua University designed the BSA program with one absolutely crucial mission: to break through industry technical bottlenecks. This isn't just about sitting in a classroom and learning existing theory. It's about actively equipping students to solve the very real roadblocks that are currently slowing down modern chip manufacturing. To pull that off, they rely on a highly specific structure. That brings us to Section 2, the PSI platform framework. This PSIG platform is anchored by a dedicated industry academia research expert coaching team. They train students across 4 major professional domains. Okay, so P stands for semiconductor process and yield management, which is really the lifeblood of manufacturing efficiency. Then S represents frontier technology and intellectual property strategy, making sure students know how to not just invent, but protect those inventions. I covers AI smart vehicles and sustainable medical technology. And rounding it out, G stands for semiconductor global operation strategy. It's the whole shebang. Now let's zoom in a bit for Section 3, green semiconductor manufacturing. Within the massive world of chip manufacturing, the BSA program zeroes in on one incredibly tricky area: the semiconductor cleaning process. Historically, this has been one of the absolute most resource-intensive bottlenecks to make environmentally friendly. So it begs the question, how exactly do we solve the most challenging bottlenecks in the semiconductor cleaning process? Well, the industry, academia, research expert coaching team has an answer. They guide their students using advanced membrane-based carbon capture technology. By deploying this really specific solution, they take that massive cleaning bottleneck and apply a cutting-edge chemical engineering fix directly to the problem. It's a real game changer. And that takes us right into Section 4, the carbon capture process. Let's roll up our sleeves and walk through this step by step to see exactly how it works in a real, functioning fabrication plant. This whole thing is a sophisticated 5-step workflow. First, identify point sources. Second, analyze exhaust gas. Third, membrane separation. Fourth, compression and liquefaction. And finally, fifth, reuse or storage. Okay, let's look closer at the mechanics of Step 1. This step is really all about location. You have to know exactly where to look to identify your capturable CO2 point sources. For this program, the optimal starting point is capturing the exhaust gas directly from the semiconductor fab itself. You're basically intercepting the emissions right where they're created, way before they ever get a chance to float up into the atmosphere. Moving right along to Step 2, exhaust gas analysis. Now, you might be wondering, why does this matter? Well, because the exhaust pumping out of a semiconductor plant is almost never just pure CO2. It's actually a complex mixed gas, so you absolutely must understand the exact chemical makeup of this mixture. Figuring out this precise recipe is a vital prerequisite to enhance the separation efficiency in the highly technical phase that comes next. That brings us to Step 3, membrane separation. This is literally the core technology of the entire operation. I want you to think of the membrane almost like a highly advanced sieve featuring a selective layer. As the mixed exhaust gas passes through, this layer efficiently screens out and captures the CO2, just leaving all the other gases behind. It's a remarkably precise physical process. But once you've captured all that CO2, you immediately run into a totally new bottleneck: space. You now have this massive, bulky volume of gas on your hands. Step 4 tackles this directly through compression and cryogenic liquefaction. Basically, by exposing the gas to extreme pressure and freezing temperatures, it converts into liquid CO2. This radically reduces its physical volume, making it vastly safer and way more efficient to transport and store. Finally, we hit Step 5, the end game. So, what's the final destination for all this liquid CO2? It usually goes down one of 2 paths. It can be dynamically reused as a chemical feedstock, which is essentially recycling it right back into the industrial ecosystem, or it can be permanently stored deep underground through geological storage. Either way, the final result is exactly what we want: substantial, real-world carbon reduction. Now that we've seen this incredible 5-step process on the factory floor, let's zoom all the way back out. Section 5, the net zero reality. The absolute crucial takeaway from our source materials today is captured perfectly in this quote. Carbon capture is one part of a net zero strategy, not the whole strategy. As advanced and amazing as Nanhai University's technology is for training engineers to break these massive bottlenecks, we have to remember it's just one piece of a much larger puzzle. And it leaves us with a pretty huge question. If this is just one piece, what other massive innovations are going to be required across our other global industries to truly reach net zero? Thank you so much for exploring this explainer with me today. Keep learning, stay curious, and I'll catch you on the next one.